Now that we know what inverses are, let's see how we can compute them. The first method that we'll talk about is actually Gauss-Jordan method to compute the inverse. This might sound a bit weird to you, but let me motivate it by saying that what Gauss-Jordan elimination is doing, as you remember, is to get to the solution of a system of linear equations. So if A is a square matrix, and if there is a unique solution, A becomes I in the RREF, and you get the solution right away. But we also saw that AX equal to B, the solution is actually A inverse B, X equal to A inverse B. So you can see that there is some kind of connection between solving equations and finding the inverse. And this method of finding the inverse using Gauss-Jordan just makes that connection explicit. So what we will do is to take the matrix A, augment it by the identity matrix, and just perform RREF on the augmented matrix. So A is an n by n matrix, I would be n by n, so AI is not A with one extra column. Now A is augmented with a full identity matrix, so it's a wide matrix, it's 2n columns, so it's n by 2n. Then you just run the Gauss-Jordan algorithm on it, you get the RREF of it. And if A is invertible, then that part will become I, because you will have enough pivots, and then pivots can be scaled to 1, and then pivots can be used to get rid of things on top of the pivots, etc. You know how that works. And that part will become I. And if it does become I, what is left behind on the augmented side will be A inverse. And this is actually a predictably deterministic algorithm and a very efficient one to compute the inverse. As you remember, Gauss-Jordan elimination is basically performing a series of row operations. So each row operation is like an elementary operator. So you have a series of them. You can multiply them to get one elementary matrix that will implement the whole of Gauss-Jordan elimination in the row picture. So it's a matrix multiplying on the left of A to give you its RREF. So what I can say is this. If you have three matrices D, B, and C, all of which are square, I can say that D times B augmented by C, meaning B and C standing side by side, is the same as DB times DC. So this is a block multiplication picture, and this will come in handy for our proof. Notice that BC is a matrix with n rows and 2n columns. D is a square matrix, n by n. So multiplying them, what you will get will be the number of rows of the first matrix and number of columns of the second matrix, 2n. So this is n here and 2n there. No issues there dimension wise. Okay, so let's look at the proof, which is fancy. First of all, we are performing Gauss-Jordan on this guy. We know that A, because of Gauss-Jordan, will become I. We don't really know what I becomes at this point. Let's call it a matrix M. It becomes something. It has to change. We don't know what it changes to. Well, we know the first statement here is a transformation. You're applying a series of elementary operations, all of which can be codified into one matrix, and then instead of this arrow, I can have an equal sign. Something multiplying this n by 2n matrix will give me the right hand side because it's a series of row operations, which is what a multiplication of a matrix on the left will do. So I have an equality. Now I see that this is in the form of my block multiplication. So we saw in the previous slide, DB augmented by C is DB augmented by DC. So let's apply that here. This guy here, E times A augmented by I becomes EA times EI, which is E. Then on the right hand side, we haven't done anything. It is just IM as it used to be here. Now we have a matrix equation here, two matrices being equal. What does that mean? Each element will have to be equal between the left hand side and the right hand side, and each block, for the same reason, will have to be equal. So the first n by n block, EA, will have to be I, and E will have to be M. Now what's E now? That's a tricky question. We already know that EA is equal to I. So what's E? Something multiplying A has given you I, so that something has to be the inverse of A. So EA equal to I implies that E is A inverse. But we know by comparing the matrices in this step that E is actually M. In other words, M is A inverse. So interesting proof. It looks a bit too easy, and for that reason you may not be completely convinced about it, but this is true. This is the way things work in linear algebra, because there's a whole machinery that we have built in the last 4.5 weeks standing behind each one of those statements. That's why these statements are compact and almost too good to be true. Not convinced, right? So let's actually do this once more in a slightly more kindergarten fashion. First step, we saw that Ax equal to B basically means X is A inverse B. We also saw that augmented matrix AB, when you do RREF, will become IB prime with the result that X is actually B prime. This also we saw. So B prime is a solution A inverse B. Now let's take a special B, B1, which is a column matrix 1, 0, 0. So in our equation here, Ax equal to B, I'm taking a special B, which is just the first column of the identity matrix. So what happens to my solution? We know that our solution is A inverse B, so it is A inverse B1. And what's B1? B1 is 1, 0, 0. By the column picture of matrix multiplication, what does that give you? It gives you the first column of A inverse, because that linear combination basically says 1 times the first column of A inverse, 0 times the second column, and 0 times the third column. So 1 times the first column of A inverse, and B1 basically picks out the first column of my A inverse. In other words, when I augment A by B1 and then I find I B1 prime, B1 prime is actually just the first column of A inverse. Similarly, I can take B2, 0, 1, 0 and B3, 0, 0, 1, and those will give me the second and third columns, B2 prime and B3 prime. So what do I have? If I take A B1, I get I B1 prime, which is the first column. If I take A B2, I get I B2 prime, which is the second column, and so on. But if I have B1, B2 and B3 standing side by side, doing the Gauss-Jordan elimination on this and doing it on A B1 is the same, because Gauss-Jordan elimination basically will find pivots in the A part of the augmented matrix, and the B part, the constant part, is just coming along for the ride, and that does get transformed into the first column, second column and third column of A inverse. So I can do all those things together. I can put those guys together in one augmented matrix rather than 3 separate ones and doing the same things over and over again, because the steps of making A transforming into its RREF, the steps are going to be the same. For B1, B2 and B3, I can do all those steps in just one go. That means I will augment A by B1, B2, B3. And what's B1, B2, B3? That is just the identity matrix, because B1 is the first column of identity matrix, B2 is the second column, B3 is the third column. What do I get after the RREF? I get B1 prime, B2 prime and B3 prime. Those were the first, second and third column of A inverse. So that's how it comes about. This I did only for a 3 by 3 matrix, but the same will apply to any number. Instead of calling it 1, 2, 3, I can call it 1, 2, n, up to n. The idea will be the same. There's no difference. So this is another way of proving it, a lot less sophisticated than our matrix method, but this at least tells you why this is actually true. But I would prefer to see the matrix proof, matrix algebra proof, and that is the right way of doing it. The reason why all these things were hidden is because the matrix algebra is so powerful that all these things were standing behind the statements that you made in the matrix algebra proof. So that is the first method of computing the inverse. Then there is a cofactor method of computing the inverse. This I'll go through first. You remember minors and cofactors. Minor of A11 is the determinant of the submatrix that you get by deleting the row containing that element and the column containing that element. So you get a matrix of 1 row less and 1 column less, and then associated with that is a sign -1 to the power I plus j. Minor with the associated sign is what we call the cofactor. In other words, mij, the minor for aij is the determinant of the submatrix, is the determinant of the submatrix. without the ith row and jth column of A. So minor with the sign is cofactor. So this is by way of refreshing your memory. Now let me define something called an adjugate matrix and its use in computing inverse. So cofactors are minors with signs. Minors are determinants, so they're just numbers. So if you can compute the cofactor Cij indexed by the row number and the column number, and you can put them in a matrix. Since each cofactor corresponds to an element in the original matrix, you can also arrange the cofactors in a matrix. It's a cofactor matrix C. Take the transpose of this matrix. It is known as so many different things: adjunct, classical, adjoint, adjugate, etc. Since it's got so many different names, I presume that mathematically this is an important matrix. But in our case, we're using it to define an inverse. You can compute the inverse using this adjugate matrix. So even though it's got adjunct, classical adjunct, and adjugate, multiple names, we're going to use the name adjugate, in our case, adjugate matrix. So inverse of a matrix is defined by its adjugate matrix. All you have to do is to take the transpose of the cofactor matrix, which is the adjugate matrix, divide it by the determinant of A. So you see that the determinant of A comes in the denominator. And that is the reason why if the determinant is 0, it cannot compute the inverse, and it means the matrix is singular. So it's a compact statement defined in terms of cofactor, but remember, cofactor is minor. Minor is a determinant, and determinant computation is actually quite expensive. So you have to do so many determinant computations here. So this computationally is not an easy thing to do. So this is not the way it is implemented. A much faster way is the Gauss-Jordan elimination method. Just augment A with I and then run the Gauss-Jordan algorithm. If the first part becomes I, the second part is the inverse. If the first part doesn't become I, it becomes something other than I. That basically means that the matrix cannot be inverted. So if it cannot become I, that means at least in one row, the pivot is not in the diagonal position. In fact, there will be a 0 row in the bottom, because if the pivot is shifted in any one row, that means the last row will be 0. Determinant has to be 0. This is a compact equation, beautiful to look at, but horrible to actually do it either by hand or on a computer. Now let me tell you what the inverse of a 2 by 2 matrix is. We know that its determinant is AD minus BC. So it goes like this, AD minus BC. Cofactor, the minor here is just D. So D is the minor of A, and that comes with a positive sign. Minor of C is just B, that comes with a negative sign. Minor of B is C, that is negative. And minor of D is A, that comes with a negative. So the cofactor matrix is D minus C minus B A in columns, and its transpose is DA and minus C minus B. So its inverse is 1 over determinant of A, so 1 over AD minus BC, and then D minus B minus C A. I try to read matrices column wise because I'm a bit anal about this matrix being a bunch of vectors standing side by side. That is why I named it A, B, C, D this way. If it is easier for you to read it row-wise, which is what most normal people do, feel free. So this is the formula for the determinant of a 2 by 2 matrix, but it's probably hard to remember. But remember what you have to do. This is basically swap the diagonal elements. So A and D, you swap them. So in blue you have that. And switch the sign of the non-diagonal elements. Non-diagonal elements were B and C. You just switch the sign. You don't swap them. You just switch the sign and divide by the determinant, which is AD minus BC. So just remember these 3 steps, and that will be supremely useful for you in exams and stuff. Swap the diagonal elements, change the sign of non-diagonal elements, and divide by the determinant. Of course, this is only for a 2 by 2 matrix. For 3 by 3, etc., you have to do more complicated things. Now, associated with the computation of determinants, etc., there's one extra thing that also looks mathematically and theoretically very nice. Is a theorem called Cramer's rule. So if Ax equal to B, that is our equation. A is a square matrix, and let's say it's invertible and there's a unique solution. In other words, determinant of A is not 0. Then I can write the formal solution as x equal to A inverse B. That is good. Then you can say that each element of x, each unknown xj, is the determinant aj determinant divided by the determinant of A. And determinant of A we know, but what in the world is this determinant of aj? Where aj is the matrix A, but with the jth column replaced by the constants vector B. So you have Ax equal to B here. So you have a vector B of the same number of rows as A. Take the matrix A, replace its jth column by B, find its determinant, and find the determinant of A also for good measure. Then take the ratio Aj determinant by A determinant, and that will give you the jth component of the solution. Looks very nice, very compact, but again, determinant calculations, horrible to actually do the computation for anything more than 4 equations or 5 equations. So that brings us to the end of this chapter. So the last thing to do is to kind of wrap up the second part of the book and the course. Remember, the first part was numerical computations. The second part was about the algebraic picture of linear algebra. And let's summarize the algebraic view. By algebraic view, we meant solving the system of linear equations encoded in any matrix. So we found 4 ways of doing it. Gaussian elimination, perform Gaussian elimination on the augmented matrix AB, and follow it by back substitution, and you will get the solutions. And you may have free variables, in which case you'll have to do a bit more complicated things. The algorithm for that is to set each free variable 1 in a sequence, the rest of them being 0, and then finding special solutions, etc. But you saw that. If you don't remember, you might have to go back and watch the videos and read the textbook again and practice also. Then we saw that Gauss-Jordan elimination on AB is not very different from our Gaussian elimination, because back substitution was in effect a row operation which is encoded in the Gauss-Jordan elimination algorithm. Then we saw that Gauss-Jordan elimination, being a formal way of solving a system of linear equations, and solution method is not different from actually inverting the matrix when the matrix is invertible. Gauss-Jordan elimination gives you a way in which you can find the inverse of a matrix, and that turns out to be the best way of finding the inverse computationally. If you have the inverse of a matrix, then you can formally write the solution x equal to A inverse times the constant vector. Given any constant vector, you can always multiply by A inverse. You can always get a unique solution if there is an A inverse, which means the determinant of A is non-zero. Then we saw Cramer's rule. Again, if A is full rank invertible square matrix, then you have determinant of A, and then you can find the determinant of a matrix created by replacing the jth column by the constants vector, find the ratio, and that would be the jth component of the solution in X. Remember, X is a vector, the jth component will be given by that method. Of course, 3 and 4 will work only for the ideal situation when you have unique solutions, and also when the matrix is invertible, which means the determinant, which appears in the denominator of the inverse calculation, as well as Cramer's rule, when that is non-zero. They are both computationally very expensive and also numerically not very stable. Not good things to do on a computer, but nice things to write down in a mathematics paper. So algebra was about solving systems of equations. Next week onwards, we will graduate to something called the geometry of linear algebra, which is a much more sophisticated way of looking at the same thing, but it's a different perspective on the same thing. But that leads us to a large number of very useful algorithms in machine learning and numerical computations. So that will deal with vector spaces and their properties. Even when we did equations in the algebraic view, we saw that each equation has a shape in a space, but that space is the coordinate space where you have x, y, z coordinates, or x1, x2, x3 up to xn coordinates. That geometry is not the same as the geometry that we'll start talking about in the next week, which is actually an abstract vector spaces kind of geometry. Those are sets rather than coordinate spaces where you have shapes. You will see that starting next week. So stay tuned for the next video.